So we've now talked about heat, and again, heat is the transfer of energy from a hot system to a cold system, but we haven't talked about yet how that can actually occur. So we have to talk about energy transfer, or more appropriately, mechanisms for energy transfer. So it turns out that in general there are three types. And we'll talk about all three of these in turn, but the first type is what's known as conduction. Second one is what's known as convection. And the third one is what's known as radiation. So, what are each one of these? So let's talk about conduction first. So conduction is the transfer of energy via direct contact. So we have to have two or more systems in direct contact with each other. So for example, when you put we all have heating elements now in our electric ranges, because most of us have electric ranges, not very often, and most of them have gas stoves anymore. But let's say you put, here is your heating elements, right? And then you put, say, a frying pan on top of this. So here's my frying pan. So the way that this works is what? The heating element then gets to a high temperature. So this is going to be at T high, where initially this thing is usually going to be at a cold temperature. So this is going to be at T cold. So basically these two things are going to be in direct contact with each other. Now basically the way that this works, again, is we go back to the lattice structure of the solid here. This is at a high temperature, which means that the kinetic energy that these guys have, these guys are going to be oscillating very wildly. So they're going to have very fast oscillations as well as very large amplitudes. So the amplitude of oscillation is going to be very large. Now when I put this pan on top of this heating element, what happens then is this one is at a cold temperature, which means these guys are oscillating less rapidly as well as with a much smaller amplitude. So when I put this onto the heating element, what happens then is the atoms inside of the heating element, which are oscillating very rapidly with a very large amplitude, start colliding with these ones inside of here, which again are oscillating with a smaller amplitude. So as these things start to collide, they start making elastic collisions. Those elastic collisions cause the ones inside of the pan here to oscillate now much more rapidly with a bigger oscillation. So basically what happens then is in the small section around here, these pieces now start to oscillate with a much greater amplitude, with a much greater energy, which means that the temperature actually is going to increase. And then these next layer, so these start slamming into the atoms that are here, causing them to then oscillate much more rapidly, which causes this section to increase temperature, this section, and then finally this section. Until eventually all of the atoms inside of the material, in this case my frying pan, are now oscillating at exactly the same amplitude as which the heating element was oscillating at, which is what transfers then the energy. So here, the crutch here is that these two things have to be in direct contact with each other, and it's that direct contact via the oscillations, or these atoms inside of the material slamming into each other, which then causes the energy to transfer. So we want to know then is what is the rate at which the energy is being transferred. So let's say here I have a hot system where this is at T hot, and then here I have a cold system where this is going to be at, say, T cold. And now we're going to connect something in between the two of these. So let's put something like a rod connecting these two guys. Or as when we were talking about earlier with that video, let's say I have a hot system with a cold system, and I'm going to connect these guys with some sort of material like a spoon. Okay. Good. So let's say some things about here. So let's say that this rod here has a length of L. Let's say that it has a cross-sectional area here of A. So in this case, we then have that what? So what are going to be things that are going to influence the rate at which energy is transferred from one side to the other side? So basically what I'm looking at is what is the power, right? So what are things that are going to influence the power? Well, one thing is that we can say is what? What happens, or the rate at which energy is going to be transferred, if I increase the length of the rod? So in the comments below, write what you think. So if I increase the length of the rod, is that going to cause the power to increase or decrease? So meaning, is the rate at which energy is going to go from this hot source to this cold source, is that going to increase or decrease? So is it going to move, is that energy going to move faster or slower? So in the comments, right, I'll give you a moment. If I increase the length of the rod, should this quantity go up or go down? Did you put your answer? Good. No lying. So in this case, what we can expect is what? If I increase the length of the rod, what should happen then is it's going to take more time, or it's going to move much more slowly. So the rate at which it's going to go from one side to the other side is going to what? Decrease, where if I shorten the length of the rod, then the time it would take for it to go from one side to the other, or the rate at which it's going to carry through, should then decrease. So what that tells me then is that what? The power, or the rate, should be inversely proportional then to the length. So again, if I increase the length, power should go down. Decrease the length, it should go up. What about the area? So in this case, if I had a small cross-sectional area versus a large cross-sectional area, would a large cross-sectional area increase or decrease the rate at which it is carried through? Or again, would the rate then increase if I increase the size of the area, or would it decrease if I increase the size of the area? So again, in the comments, write your thoughts. So what should happen is if I increase the cross-sectional area, so if I went from a cross-sectional area like this to a cross-sectional area like this, the rate should increase because now I'm allowing more energy to pass through because I now have a much greater cross-section, as opposed to what, if you think like I'm trying to put water from one side to the other side, if I have a lot of water hitting here, it's going to what, have to funnel down, and I can only allow a few things to go through as opposed to a lot. So in this case, this would have to increase if I then increase the cross-sectional area. What about the change in temperature? So let's say I had a large temperature here and a very small temperature here, so that there was a large, what's known as temperature gradients. Okay? So would having a larger temperature gradient increase the rate at which the energy is delivered, or would having a small temperature difference increase the rate at which it's brought? So meaning, if this was at 100 degrees Celsius and this was at 0 degrees Celsius, would the rate of energy transferred from the 100 to the 0, would that be bigger or smaller than if this was at 1 degree versus 0 degrees? So again, in the comments, I'll let you think about that and write your expression. So, turns out that if I have a bigger temperature difference between the two, or a larger temperature gradient, that's then going to increase the rates at which the energy then is going to be carried through. So in this case, we can then say the power, which is equal to the heat divided by the time, is then equal to what? The cross-sectional area, or at least, let's write this as proportional to, so here's my proportional to, cross-sectional area divided by the length times then the change in time. So this thing is actually given by K times A divided by L times the change in temperature. Okay. So this is then the rate at which energy is carried through in conductivity, or in conduction, which is two things or more things in direct contact with each other. So again, A here is the cross-sectional area, L is the length, delta T then is what? The change in temperature. Sometimes you'll see this written as delta T divided by L, which is, again, what's known as the gradient. So it's the temperature difference per unit length. And then K here is what's known as the thermal conductivity. So different objects have different thermal conductivities. So as we can see from here, the larger the thermal conductivity, then the larger the rate is going to be, which means that the energy is going to transfer faster. So for example, again, going back to my spoon here is made out of metal. Metal has a very high thermal conductivity, which means it's a very good conductor of thermal energy, so it's going to allow it to move through very quickly. As opposed to something like, what do I have in here? Do I have any wood in here? I have wood somewhere. But anyway, something like wood has a very small thermal conductivity, which means it doesn't allow energy to transfer very rapidly, which means it's not going to let the energy go from one side to the other side very rapidly. Also, if you think about things like inside the walls, there's insulation. My insulation then is there to have a very small thermal conductivity because I don't want the energy that I put into my house, for example, in the summertime. I don't want my cold house on the inside to lose energy or actually have energy come from outside into inside, causing my house to heat up, which means I'm going to pay a gigantic electric bill trying to cool down my house. Or in the wintertime, the opposite, where I'm trying to heat up my house. I don't want all that energy to leave to the outside system, outside world, causing the world to warm up. I don't want to pay for that, right? So in that case, something like insulation is also going to have a very small K value. So for thermal conductivity, if I want to not have a very large transfer of energy, I have to have a very small thermal conductivity. If I want to have a large transfer of energy, in that case, I have to have a very large K value. So in this case, if I want to know the total heat which flows from one side to the other side, all I have to do then is multiply both sides by the time. So this is going to go as K times A divided by L times the change in temperature times the time. So this is then the amount of energy I have transferred from one system to another system in a given amount of time. So this is what we call conduction. So again, conduction is the transfer of energy via direct contact between two systems where one is at a hot temperature and one is at a cold temperature. So our mechanism for heat transfer. So before we move on to conduction, let's do a quick example of this, just kind of see how this actually works. So this example says that we want to find the energy transferred in 1 hour by conduction through a concrete wall, where this is my concrete wall, which in this case is 2 meters high. This is 2 meters high. This is in this direction, so long. Let me just call that little L for length. We call that height. Length in this case then is 3.65 meters, but this thing also has a thickness to it. So here is my thickness of my wall. Great. Where this thickness of the wall then is equal to, let's call that T. I'm going to call that T, not that T either. I don't know, what should I call that? So I got length, width, let's call that the width. There we go. Width is equal to 0.2 meters. In this case, then the thermal conductivity of concrete is equal to 1.7 watts per meter per Kelvin. Okay. Now, in this case, let's say this is inside, so T hot is going to be equal to 20 degrees Celsius, and this happens in the wintertime, so outside T cold is equal to 5 degrees Celsius. So again, what I want to know then is, what is the energy, or how much energy is transferred in 1 hour? So good. So basically, we're just going to use this expression. So now we know that the energy which is transferred in 1 hour then is going to be equal to K times cross-sectional area divided by the length times the change in temperature times the amount of time. Okay, now I can get rid of all this stuff. Good. So we know K, so now we have to determine the cross-sectional area. So in this case, the cross-sectional area then is going to be simply this cross-sectional area, which means in this case, we were trying to transfer energy from one side of this to the other side, and the length in this case is then simply going to be equal to the width. So it's going to be the same thing then as K times the area, but the area in this case then is simply going to be what? The length times the height, divided by the thickness, or the width, times the change in temperature, which is simply going to be T hot, minus T cold, times the time, where the time in this case is what, 1 hour, so that's 3,600 seconds. So good. Plug in my numbers. What I find in this case then is this works out to be about 3.35 times 10 to the 6th joules. So basically, what this means then is what? If my house was purely made out of concrete, and in the middle of the wintertime, if I had it at 20 degrees on the inside and it was 5 degrees on the outside, in 1 hour, I'd be losing 3.35 megajoules worth of energy in an hour. That's how much energy would be transferred from the inside of my house to the outside, which means I have to supply that energy back to keep this at 20 degrees. Right? Otherwise, what will happen then is this thing will slowly have its energy go down, meaning its temperature go down, until these two things will reach thermal equilibrium. Good, so that's the first one. So that's conduction. So the next one we're going to talk about is convection. So what's convection? So convection then is the transfer of energy via the motion of a medium. So for 2, so convection is via the motion of a medium. So what does that mean? So that means that, for example, let's say it's in the summertime, late at night, so you build a fire, right? So let's build a fire. So here's going to be my fire. Put some orange in there, some blue down here in the bottom, right? So this is my fire. Great, so what am I going to do? So let's say I put my hand some distance above the fire, and then I feel warmth, right? My arm, in this case, starts to actually heat up due to the fact that I have it above the fire. So how is this actually working? Well, this is working because the medium itself, i.e. the air, is actually flowing past my arm, and my arm is actually heating up because the air is carrying that energy to my arm. So what's actually happening here is that what? The energy is brought to me by convection due to the fact that air is actually moving past my arm, and that air is warm. Right? So how does this actually work? Well, this works because here I'm in a fluid. So what happens here is the fluid of the air, right? So the density of the air around this object has a particular density. But the air, which is very close then to the fire, what happens in that case then is the kinetic energy increases due to the fact that it's right next to the fire. But as the kinetic energy increases, the intermolecular distance between the air molecules increases, meaning as I give them more kinetic energy, they actually move further apart. As they move further apart, what happens in that case then is the volume is going to increase, which means that the density here is going to decrease. Right? So basically, the density of the air here, so let me call that density 1, versus the density of the air out of this little pocket of air, density 2, the density of the air here, 1, is going to be less than the density of 2. Right? So the density of 1 will be less than the density of 2. And as we talked about last chapter, what happens is what? If I have a object of lower density in a fluid which has a higher density, that object then has to accelerate upward because of the buoyant force. So this thing is going to have a buoyant force. That buoyant force then is going to point upward, which means that this thing is going to ultimately accelerate upward. Again, due to the fact that this density is different, is now less because of that increased temperature via the fire. So this pocket of air then is going to accelerate upward, and it's going to accelerate past my hand, and as it accelerates past my hand then is going to transfer energy, actually via conduction in this case, because now the two are in direct contact with each other, but ultimately because of this convection of the air actually moving through. Now, what happens then is that this air is going to keep moving up, which means that this air here, which was at an initial density of rho 2, falls down into this location because it's heavier, so now it's going to fall downward, which means that that's going to heat up, reach a density of rho 1, and then go back through. So this is actually going to be a cyclic process because this original air here is going to move all the way up into the upper atmosphere. It's going to expand out so much that eventually it's going to become part of the same density as the air around it, and then eventually it's going to fall back through. So this is actually going to make a circulating system where this air is always going to constantly fall back through, get heated up, and then create this circulation moving past my hand, causing my hand to actually move up or increase in its temperature to get warmer. This is the same thing happens in a convection oven. Now, to increase the temperature or increase the speed at which something is actually cooked, then you turn on a fan on the inside. So in your convection oven, what happens is it actually circulates the air on the inside. That air then can move into more easily the object at which you're trying to cook and cook it more evenly through and cause the rate at which it's going to cook to actually be faster. Now, this also explains things like sea breezes, right? So if you were at the sea, so let's say here's the beach, right? So here's the beach, and then here is the sea or the ocean, right? So what happens then is what? You get this idea of convection as well, where what happens then is what? During the day, when the sun is blasting down on the sand, sand has a much lower specific heat than the water does, which means that the temperature of the sand, because the hot temperature, or the temperature over the water becomes the cold temperature. So what happens then, again, is that the density of the air here is less than the density of the air here. So this air then wants to move from a, what? High pressure, because this is going to create a high pressure, to low pressure. So basically all this air which is here is going to get pushed into this direction over the water, where it's going to cool down. As it cools down, it's going to move back into this area and then basically do the same thing. So what will happen then is that what? During the day, the wind will blow from the beach into the water, and then make a circulating fashion in this case. Now, at night, what happens again is that what? Since the beach itself has a much lower specific heat than that of the water, what happens then is at night, the beach then is going to become the cold temperature because its temperature is going to drop much further than that of the water. The water then is going to become the high temperature. So again, it's going to have that the air here is going to be at a less dense, at a higher pressure. So it's actually going to move into this direction. As it moves above the beach, it's going to cool down, gets pushed back up, and then it's going to come back over the water, heat back up, and then do exactly the same process. So what happens then is what? During the daytime versus during the nighttime, if you're standing on the beach, the direction at which the wind is blowing is going to reverse. So during the day, it's going to go from the beach out to the water, and then at nighttime, it's going to go from the water to that of the beach, all via convection. So we're not going to write down anything mathematical with convection. It's more just simply an idea, but this is convection. So it's the transfer of energy via the motion of the medium itself. So finally, that brings us to radiation. So we mentioned this before when we were talking about temperature, but everything radiates. So anything which has a temperature gives off light, i.e. electromagnetic radiation, and that radiation can be used to warm something up or cool something off. So, for example, if I was, say, staying here with radiation, so this is the transfer of energy via light. And so what happens is if I was standing here, I would then be giving light off in all possible directions. So when I'm at a high temperature, I'm now giving off light in basically all directions, but I don't do this perfectly. So turns out that different people and different objects give off light and absorb light in different ways. So we have two different distinctions. So one is what's known as a black body. So black body versus a perfect emitter. So a black body is an object which is a perfect absorber. So what it does is any light which is coming into it, it completely absorbs it and doesn't give anything off. It just fully absorbs and never gives off light itself. A perfect emitter is something which doesn't actually absorb, it only gives off light. Okay? So it turns out for both of these two, even though they're kind of slightly different, the power or the rate at which energy is actually given off is then given as what's known as Stephan's constant times the cross-sectional area times temperature to the fourth. So if I was talking about a black body, then the rate at which energy is absorbed by that black body is given by this. And if I was talking about a perfect emitter, the rate at which the energy is emitted is given by this as well. But for something like me, I'm not a perfect black body and I'm not a perfect emitter, so I'm going to be somewhere in between. So for any typical object, it turns out that the power, or the rate at which energy is given off, is given by this epsilon times sigma times A times e to the fourth, where epsilon here is what's known as the emissivity. Where emissivity is basically a measure of the object's difference between a black body or a perfect emitter. So, depending on the radiation here, so this is either the radiation which is absorbed or the radiation which is emitted. Depending on which way I'm talking about this, the emissivity is going to be anywhere from 0 to 1, depending on which direction. So if I'm talking about the radiation which is being emitted, it's going to be 0 for then a black body, and then 1 for a perfect emitter. Right? But again, us as people, or basically anything, it's going to be somewhere in between. It's going to be somewhere between 0 and 1. Now, simultaneously, I'm giving off radiation, but I'm also absorbing radiation simultaneously. So I also have radiation which is coming in. So this means then that the total power then is going to basically be different, or the difference between the power that I absorb minus then the power that I emit. So in this case, let's assume that my emissivity is the same, Stefan's constant is the same, my cross-sectional area is the same. So what this means then is that this is going to be the emissivity times then Stefan's constant times the cross-sectional area times the temperature at which I am absorbing. So that's going to be the temperature of the environment. I'll write that as environment to the fourth, minus then the temperature that I'm emitting, which is my temperature to the fourth. Now, what does this mean? So this means that what? If my temperature is greater than the external temperature, this power, the total power, which ultimately in this case is going to be the power that I absorb, will be negative, which basically means that I'm not going to absorb power, I'm only going to emit power. So for example, this is what happens when you go outside in the wintertime. So in the wintertime you go outside, your body temperature is greater than the temperature outside. So in that case, this is why you cool down. One of the reasons why you cool down is because all the lights that you are emitting off is going to the exterior. Sure, you're absorbing some stuff, but the temperature is so much lower, you're not really absorbing. Overall, you end up giving off energy. So that's one of the reasons why you cool down. As opposed to in the middle of the summertime, then the temperature of the environment is typically going to be greater than your temperature. So in that case, this will become positive, which means that you're absorbing more power than you're radiating off, which means your temperature ultimately is going to increase, which is what makes you usually kind of uncomfortable. So this is one of the reasons why your temperature increases. So Stefan's constant it is a constant. So let's write down what that constant actually is. Good. So Stefan's constant, I'll write that down here. So sigma is equal to 5.67 times 10 to the minus 8. This has units of watts per meter squared per Kelvin to the fourth. Because again, this thing has to have units of watts. Emissivity is a dimensionless quantity, so this has watts over here. This side has to be as watts as well, but this is an area, so that's meters squared times Kelvin to the fourth. So this has to have the units to kill those guys off. So good. So these are the 3 ways that we actually give off or can transfer energy from one system to another. Again, we have conduction. Conduction is the direct contact between 2 or more objects. Convection is the flow of the medium itself past an object. And then finally radiation, that is the electromagnetic radiation, which is actually given off. Now a good example of putting these guys together is what's known as a Dewar flask, or simply a thermos. So let's talk about a thermos. Let's talk about how a thermos is actually designed with all of these things in mind. So let's talk about that Dewar flask. Dewar flask, also known as the thermos. So here we're going to have a neck of it. And it's going to come down, say something like this. And this is then my Dewar flask. Now, typically, the way this is set up is that there is going to be a hollow wall between the exterior and interior. So where you actually keep your hot, tasty soup or your hot, tasty beverage. So, for example, if you made coffee in the morning and you put it in a flask, you want that to stay hot for most of the day. Or if your wife makes you hot soup, or your grandma or your mother or whoever makes you soup and you want to bring it in with you, you want that thing to stay hot. You don't want it to become lukewarm, right? So typically what happens is then there's a layer between the inside portion, which is where you're going to keep your tasty object, and then the outside portion, which is going to save it from the wall. Now, here, there's a few conditions. So inside of here, what you usually do is this inside wall, you try to vacuum out. So you want to make sure that that is a vacuum. So this has to be then airtight. And then you also silver the walls on the inside. So basically inside of here, you're going to silver them, or at least put a mirror inside of here. So you want to put a mirror or silver them. Of course, putting a mirror is a little bit cheaper than silvering. So if any of you ever worked in a catering or in a food service, and you have those big pots of coffee that you would push, right? So you push the top and then the coffee comes out. Typically inside of those there are mirrors. So I used to work in catering, food service, and every once in a while you drop one or hit one and then all of a sudden you hear the shattering, so you just broke all the glass on the inside, which kind of makes it pointless. but basically you line the inside with either, again, silver or some sort of mirror. And then here, what you try to do is you restrict the size of the neck, so you decrease the size of the cross-sectional area. So decrease cross-sectional area. So, question is, well, why go through all this work? Well, you go through all this work to basically, again, make sure that your tasty beverage or your soup or whatever it is that you have inside of here stays at least as hot as possible, or again, as cold as possible. I could put cold stuff in there too, and I want to make sure that it stays cold the entire time. So what do each one of these different things supposed to decrease? Well, in this case, the vacuum is to decrease conductivity. Because in this case, what you're trying to do is set K equal to 0, right? So that's coefficient, that thermal conductivity, that K value, for a vacuum, since you're basically taking out all the air, there's nothing in between, which means that you're trying to reduce that K value basically down to 0. So in this case, you're trying to take out conduction between these two walls by not putting any medium on the inside. Why silver the walls? Well, because if I have something hot on the inside, it's going to radiate, and as it radiates, I'm going to have light try to come out, right? So it's going to pass through this wall. But what does the mirror do? Well, the mirror then is going to cause this radiation on the inside to reflect, and as it reflects backwards, it's going to hit this inside wall, which is also mirrored, so it's going to cause it to reflect. And what you're trying to do is cause the radiation on the inside to basically just reflect and stay within inside of this interior wall. Now, of course, this only works so well because typically mirrors or silver aren't 100% reflectivity. They don't reflect things 100%. They're going to reflect things anywhere typically from about 97% to about 99%. Okay? So, again, it does a good job. 97% to 99% is very good, but again, you have that anywhere from 1 to 3%, which is still going to go to the outside, which eventually will cause the object to cool down. Why decrease the cross-sectional area? Well, this is to reduce radiation. This is then to reduce convection. So here, what happened is when you open up the lid for this, steam is going to come out, right? So as the steam comes out, you're now carrying away energy via the convection of the steam, which is actually carrying out. So if you make the cross-sectional area as kind of small as possible, or at least smaller, then the amount of steam that you're letting come out, the amount of energy which is now losing is going to be at least somewhat minimal, right? As opposed to if I had a very large cross section, then I have a lot of steam which is coming out, carrying a lot of energy away, as opposed to a small cross-sectional area. So the Dewar flask or the thermos is a great example of all of these things basically put together to, again, try to ensure that you have something hot to either eat or drink at some later point of day, or again, something cold. Right? I could put something cold in there as well. But again, it's designed to minimize the amount of energy transfer via all three of these components in conduction, convection, and radiation.